Welcome everybody to this session on Azure SQL Database Serverless. My name is Morgan Oslake. I'm a program manager on the Microsoft Azure data team. In this session, I'd like to begin by discussing what Azure SQL Database Serverless is, and then move on to discuss when and how to use it in order to best price and performance optimize your applications. But before getting into the details of serverless, it's useful to first step back and consider some of the challenges facing developers when price and performance optimizing their applications. So consider a typical scenario of an IoT application with a centrally managed database that collects rainfall data from thousands of geo-distributed weather stations, as well as exposing endpoints to clients to connect to in order to run various analytic scenarios as well as generate reports. Now, you can imagine that when the weather is relatively calm, the usage on the database is relatively low. But that say when a storm system passes through, the usage on the database can increase suddenly and to rather high levels of compute. So the key point to emphasize here is that the workload demand on the database is unpredictable, both in terms of its amplitude as well as its timing. This presents DevOps challenges in terms of how best to size the compute for the database in order to achieve your price and performance goals. One option is to allocate compute that's sufficient to accommodate the peak workload demand. But then given this spotty usage pattern, there'll be periods of time where there are wasted resources, which ultimately leads to higher costs. On the other hand, you could decide to provision an amount of compute that essentially matches the average usage over time. But then, of course, during periods of peak usage, performance can be poor and suffer and lead to customer dissatisfaction. If the database is already in the cloud, then you could take advantage of that compute elasticity and build rescaling automation. But that, of course, incurs development costs, maintenance costs, as well as added operational complexity. So that's exactly the kind of scenario that serverless is intended to address. Serverless in SQLDB essentially provides two key scaling capabilities. First is its ability to automatically scale compute over a range that's configured by the customer in terms of the minimum and maximum number of cores that are also an index into the range in memory that the database can scale between. And then the service takes care of providing whatever amount of compute in terms of CPU and memory is required to satisfy the workload demand of that database. The second key capability of serverless is its ability to automatically pause and resume. So in this scenario, the customer is able to specify or configure the auto pause delay, which is essentially the length of time that the database needs to be idle before the service will take the opportunity to automatically pause the database. And then when workload activity returns, the service will automatically resume the database. And in the meantime, the database, while it's in the pause state, has terminated its underlying compute and resulting in some additional cost savings. So in terms of billing, serverless charges for the amount of compute used, and both in terms of CPU and memory on a per second basis. This is to be contrasted with the provision compute tier set of choices in SQLDB, which allocate a fixed amount of resource for a fixed price and charges for that resource independent of its usage on an hourly basis. And then, as I said before, if the database is paused because that compute is terminated, only storage is billed for even greater price savings opportunities. In terms of the kind of usage patterns that are the best fit for serverless, you can think of them as being broadly characterized as intermittent and unpredictable. So imagine, for example, a pattern where the compute demands have episodes of bursting activity, perhaps to some high number of cores, but that in the intervening periods of time, the usage is relatively low or idle. That's an example of a pattern that tends to have a lower uh, compute utilization average over time, and for pricing reasons alone would lend itself, would be a good fit for serverless. Serverless can also be a great starting point for any new database that doesn't have any usage history, when it's difficult to sort of predict ahead of time what those requirements might be. And if for whatever reason later on, serverless doesn't appear to be a good fit for, say, pricing and performance reasons, the database can easily be moved out of serverless and over into the provision compute tier. Otherwise, in terms of the rest of the management capabilities in serverless, they're the same as they are for provision compute. So for example, high availability is built in, backups are automatic, updates and patching are automatic. Machine learning is running in the background to provide performance tuning recommendations, as well as recommendations to optimize security. So with that, I'd like to first demonstrate onboarding into serverless. So here I'm showing the Azure portal for SQL DB. It has 6 databases, and many of these databases are in serverless. Some of them are paused. But what I'd like to do here is create a new database in serverless. So I click this button called plus create database, and this will bring up a new page with metadata that's largely pre-filled. All I really need to do at this point is specify the database name. Then I click this link called configure database, and you'll see you're presented with 2 choices to create the database in provision compute or serverless. So I'll click serverless. And now you can see that there are these 3 configuration parameters that we discussed before: the max number of cores, the min number of cores, defining the compute range for scaling, and then the auto pause delay. So I can adjust the maximum number of cores all the way up to 40, which is uh, how far the database can scale up to. I can also make adjustments in terms of the minimum number of cores, which is a contract with the service that means that the compute will never be scaled below that amount for perhaps certain performance reasons. Then I can also make adjustments to the auto pause delay, which again is this period of time before, or that has to elapse before the service will pause the database. Now, it could be, for example, that for my application, um, I don't want the database to pause over the lunch hour during the work week, so that when the users of that database come back from lunch and reconnect to that database, they don't have to experience any kind of performance penalty while that database is warming up again. So maybe I adjust the auto pause delay from an hour to, say, a couple of hours. But by doing so, my database is still able to benefit from pausing, say, at night and on the weekends. If the database, on the other hand, is sensitive, say, at all times to pausing and resuming, I can disable that altogether and still benefit from automatic scaling over this min and max vCore range and paying just for the amount of compute used on a per second basis. And once I've made those configuration decisions, I hit apply, and you're off to the races. So in terms of scaling, here I'm showing an example of a serverless database that's configured with a min of 2 cores and a max of 16 cores, corresponding to a range in memory from 6 to 48 gigs. Now, suppose that at one point in time, the database needs to load a lot of data into its cache. Say, for example, it's performing a table scan. Then service is able to adapt to those memory requirements, even if the CPU usage is rather low. On the other hand, let's suppose that at some later point in time, the nature of the usage pattern shifts to become more oriented towards computationally intensive operations. Then again, serverless can adapt to relaxing the amount of memory that's provided and then increasing the amount of cores that's provided. The key point here is that whatever combination of CPU and memory is required by the application based on its own workload demand, the service is able to deliver. In a sense, you can think of the memory to vCore ratio in serverless as being dynamically adaptive based on the actual workload demand of the application. In terms of scaling latency, suppose, for example, at one point in time, the database is using 2 cores, and then at the next moment in time needs to suddenly burst to 16 cores. That scaling speed is typically very fast in under 1 second. There can be occasions where that scaling speed takes on the order of a few minutes, but that's only if load balancing is required internally by the service, which is a much more rare occurrence. And we'll talk a little bit more about that later in this session. Now, this is a very different picture than, say, scaling with provisioned compute. In provisioned compute, the burden shifts to the customer to specify upfront what their compute requirements are. So suppose the customer has determined that they need 2 cores of compute for their application, they'll automatically be provisioned 10 gigabytes of memory. And that's good in the sense that the customer has the assurance that those 2 cores and those 10 gigs of memory are continuously allocated for all time. There is no reclamation of resources in the background, and the potential for compute warmup that could follow that does occur in serverless. On the other hand, those 2 cores and that 10 gigs are being billed regardless of whether or not they're actually being used. So in a sense, there's a pricing penalty here. Then suppose later on for the same database that 2 cores are insufficient to handle its workload demand. Here, the burden again shifts to the customer to first detect that condition and then identify whatever number of cores might be required to satisfy that increase in usage. And then once that's been identified, the customer initiates the scaling operation, which takes at least on the order of a few minutes, if not longer. And at the conclusion of that operation, connections are always dropped, which represents a brief disruption to availability. This can happen in serverless as well, but only if load balancing is required, which again, as I said, occurs very rarely. Most of the time, that scaling is very fast with virtually imperceptible impact to the customer performance experience. So next, let me demonstrate auto scaling in serverless. So here I have a database called DB1, and you can see from the name of its service objective that it's in the general purpose tier. S stands for serverless. It's on generation 5 hardware, and it has 8 max vCores configured. And what I'd like to do is drive some load against this database by running these 2 queries. In parallel. And each of these queries essentially are grabbing system objects, materializing a large table, and then performing a nested loop join. So very computationally intensive workload. And then to demonstrate how quickly serverless is able to respond to that sudden increase in workload demand, we can look at the DMV for resource stats, which reports on key utilization metrics like CPU over time. So here you can see that my query started at roughly 41 minutes and 35 seconds, and that by 41 minutes and 51 seconds, so about 15 or 16 seconds later, it was using virtually 100% of all 8 cores. So it went from essentially idle usage to bursting up to all 8 cores in around 15 seconds. And uh, that database probably actually scaled much more quickly than that. And here we're only limited in seeing that based on the resolution and the telemetry of this DMV, which is collecting and reporting on usage once every 15 seconds. So next, I'd like to dive a little bit into the architecture of serverless and then uh, connect the architecture back to the customer performance experience. So serverless is a three-tiered architecture. There's the control plane, which contains the gateway service that's responsible for authentication and managing connectivity. There's the management service that handles DDL operations like create and drop of the database. And then sitting below that is the data plane, which contain tenant rings, which you can think of as collections of virtual machines that provide the computing power for the serverless databases. And then disassociated from that and sitting below the data plane is the storage plane, which contains the actual database files located on or stored on solid state disks. So let's consider, say, the journey of a serverless database as it goes from, say, the pause state into the resumed and online state, and then begins to process workload. So the first action that may happen is that the client will attempt to connect to the database, but because it's paused, that first connection attempt will fail. So it's very important that the application have built-in connection retry logic wired into it. Then on a subsequent connection attempt, the gateway will authenticate that client, pass control over to the management service, which will identify a tenant ring and then work in cooperation with the service fabric to identify a specific machine within that tenant ring that has sufficient capacity to handle the scaling operations for that database that's being resumed. And part of that resuming process involves the underlying SQL instance that contains that serverless database attaching these remotely stored database files. And at the conclusion of that process, the database is then online and able to respond to requests. From that point forward, RG Manager on the machine is performing constant surveillance, both in terms of the usage of the machine itself, as well as each of the individual databases running on that machine. And if it detects any usage imbalances or bottlenecks, then it seeks to quickly resolve those bottlenecks and can do that virtually instantaneously and with imperceptible impact to the customer performance experience. There can be occasions where the machine is unable to sort of make adjustments to satisfy the scaling demand of the serverless database, in which case the service fabric load balancer re-enters the picture. It identifies a different machine in the tenant ring that has sufficient capacity to handle that scaling request, and then repositions one of those serverless databases over to that other machine. And that load balancing operation across machines, that's what can take a few minutes to complete, which is what I mentioned before. But again, that's a very happens very rarely, and most of the time that rescaling, automatic scaling of the serverless database is satisfied within a single instance machine environment and occurs virtually instantaneously. And then in parallel to RG Manager performing this sort of machine level surveillance, within each SQL instance of each serverless database, there's a memory manager that's constantly analyzing the usage history of the database. And if it detects that the active cache utilization drops below threshold, then it will initiate a sequence of memory reclamation operations to reduce that memory footprint. And that's a very different memory allocation pattern than, say, provision compute, where once that cache memory has been allocated, it tends to remain allocated indefinitely. And that's for good reasons. It improves the performance of the application so that if at a later point in time, the application needs data and it's already in the cache and can avoid touching disk, then that's a performance improvement. So here, this highlights performance trade-off that needs to be made when considering whether or not to use serverless. On the other hand, because serverless is reclaiming memory when that memory is not being used, we're able to pass those cost savings along to the customer. So now let's take a look at what those cost savings look like for a serverless database. So here, again, I'm showing the portal experience for a serverless database that's configured with a max of 16 vCores. You can see this chart on the lower left is showing the CPU usage over time, and there's over the last hour, and there's essentially sort of 3 bursting episodes with relatively low or idle usage in between. And each of those bursting episodes you can see track quite closely to the chart on the right, which is displaying the billable compute metric, which is measured in units of vCore seconds. So if I want to understand or estimate what the cost of the serverless database is, say over a 24-hour period, then I just need to aggregate the total number of vCore seconds billed over that 24-hour period, which is given by this quantity in the lower left-hand corner of this chart on the right-hand side. So it's telling me that the total number of vCore seconds used over this 24-hour period is 278,390. And so if I also know the compute unit price, which is expressed in dollars per vCore second and is fractions of a penny, and I take the product of that with the total number of vCore seconds, I'll come up with an estimated cost of about $40. Now, if I compare that cost to a database in the provision compute tier, also with 16 vCores configured, then over that 24-hour period, the cost for that database is $96. So you can see here that for a database with this workload pattern, the cost savings in serverless are just north of 50% relative to provision compute. In terms of roadmap, we're working on support in the hyperscale tier, which is in fact in private preview right now. And this is beneficial for workloads that require more I/O performance, for example, than the general purpose tier can provide, which is where serverless is currently publicly supported. We're also working on support in Elastic Pools for customers like SaaS ISVs that may have tens, hundreds, or even thousands of databases. We want to raise the limit in terms of compute that a serverless database can scale to from the current limit of 40 cores to at least twice that amount, if not higher. We're working on improvements in pausing and resuming to, for example, reduce the minimum configurable auto pause delay below 1 hour to, say, something on the order of a few minutes to give databases more opportunities to pass through pausing and resuming cycles and enjoy even greater price savings. We're also working on building or putting connection retry logic and building that into our client drivers. And in fact, we've done this already for SQL clients using .NET, and we're working to extend this built-in connection retry logic to other drivers as well. And then finally, we're expanding on the coverage we're providing for business continuity scenarios, including support for availability zones in serverless, which is currently in currently in a public preview with GA coming soon. So in summary, SQL Database Serverless is price and performance optimized for single database workloads with intermittent unpredictable usage. It automatically scales compute, optionally automatically pauses and resumes, and then bills just for the amount of compute used on a per second basis. So for more information, I'd invite you to visit aka.ms/SQLDB_ serverless. Thank you.